EPFL.
Thank you.
Stage is yours.
Okay. Well, thank you, Gabriele, for inviting me and for putting this great event together in such a beautiful theater. It's a pleasure to be here. So what I want to talk about is Scala 3. And the first time I gave a variant of this talk was at Scala Days in June in Lausanne, where we had the first Scala Days back in Lausanne since the start 9 years ago. And but since June, actually, quite a few things happened, and we did some last-minute changes. So this talk reflects all the changes up to today. So first, let's have a look at the roadmap. So we said in June, all features fleshed out, and with implementations in DOTI 16.0.16. And that was more or less the case. Then we said in fall 2019, we'd go into feature freeze, and we will release the Scala 3.0 M1. So that's very soon. Well, fall is flexible. We just started fall, so we still have 3 months to go. And I should probably also qualify what we mean by feature freeze. It's actually more a feature cooldown, let's call it that. Because what will have to happen after the feature freeze is that we have about a year of stabilization, feedback, and experimentation. So the feedback will come from you, the users. We will essentially put every new thing up on the contributor threads, and will also be decided by the SIP, Scala Improvement Process Committee. So essentially features have to be evaluated and confirmed by the SIP. And that means that depending on how that goes, there would still be the possibility of some changes from now to fall 2020 when we finally, when we plan to release a Scala 3.0 final. That said, we will not go overboard anymore after the feature cooldown with essentially inventing new stuff. So basically we said we have the envelope. That's the set of features that we propose. We will, depending on the feedback of the community and of the SIP committee, drop or change some of these features. But anything that we want to, any new designs will have to go in a future language. So that's the plan. At the same time, we will have the Scala 2 development, where again in June 2013 came out, and hopefully by about at the same time as 3.0, we should have 2.14. Maybe it will lag a little bit. We don't know that yet. And that will 2.14 will concentrate on essentially making the migration from the current Scala 2 to Scala 3 as easy as possible. Okay. So what I wanted to do here is to give you a quick tour of what's in Scala 3, and actually there's quite a lot. So what I want to, the way I want to structure it is to say, well, can we have a essentially best features list? What are Scala 3's nicest features? And if I ask that question, then the answer, of course, depends very much on who you are. Are you a beginner? Are you a learner who's just starting out? Are you an expert who wants power features? Are you just essentially a programmer who wants essentially everyday productivity improvements? So I have classified this list according to these 3 categories to say, well, for each category, what does Scala 3 have to offer? And of course, nobody can, not everyone agrees on it, so I give you my personal ranking, what I find most exciting and most interesting in each category. But I also did a Twitter survey and will report on that. So what people on Twitter in the survey said what features they liked best. So let's start with beginners. So at that level, actually, most of the language stays the same. But there's nevertheless a few improvements worth mentioning. The first thing that I believe will be quite important and quite pervasive is that new from now on is optional, basically. So you can just write a application like this one here, the string builder thing, without the new, and the new will be inserted for you. New can be omitted from almost all instance creations. Where can it not be omitted? Well, it's basically if you're in an apply method, let's say you want to override the normal constructor with an apply method, then if you called just the code without the new, then you would get a recursive call to your apply method. So you probably don't want that. You will probably want to escape that and actually create the object now, and that's when you will need it. And you'll also need it for anonymous classes, because that syntax is not captured by the normal function call syntax. So that means that you don't need to define a case class anymore just to get the nice constructor calls. And it seems that quite a few people did that. So they made a case class, just to get essentially the construction syntax without the new. And they didn't care about all the rest that they would get in these classes. So now that's for all types that you have. Okay. The number two improvement, I believe, is top-level definitions. So you don't need to put things in objects or classes anymore. You can just write them at the top level like this one here. So you can write a type, you can write a val, you can write a def. So that means that also that you don't need the previous construct that sort of made that work, and those were package objects. So previously you couldn't put things just at the top level, but there were these things package object that you could put them in a package object, and they were accessed as if they were on the top level. So now basically all this complication is gone. You just put them on the top level and you're done with it. Behind the scenes, the compiler will, of course, have to wrap this somehow, put it in something, so it will still make up an object transparently for you where it puts these things, but as a user, you don't need to worry about that. Okay, so that was number two. And number one for me is clearly enums. Oops. So enums are the simplest way to define new types with a finite number of values or constructors. So here's a simple example. Enum color, case red, green, blue. There you go. That was actually surprisingly complicated in current Scala. What would you do? You can write 3 vals with ints, or you can write 3 objects. That would be quite a bit inefficient in bytecode size. Or there were many possibilities. There's standard library had an enumeration type, but that was kind of awkward to use. So people didn't agree. And now there's essentially one super simple way to write this thing. But it doesn't need to stay that restricted as you see it here. You can also essentially go to everything that Java enums can do. So here you have a standard Java example that you find in the enum documentation of Java, that you want to write an enum planet. The planet has parameters, mass and radius, and then essentially each of the values, Mercury, Venus, Earth, Mars, and so on, they essentially refine that enum with specific values for the parameters. So you can do that. And you can add fields to and methods to enums. And all this works just like in Java. And it can actually interrupt with Java. So if you write something like this, if you have an enum and you let it extend the type Java-lang enum, then the compiler will actually understand that what you are defining should be something that's compatible with the Java-lang enum. So it will be represented for Java code as an enum, and Java code can call this thing as a Java enum. But it doesn't stop there either. So the next thing you can do is you cannot give enums just value parameters. You can also give them type parameters. So that's what it looks like here. So you have an enum option, which has a type parameter t, which happens to be covariant. And then it has 2 cases, some and none. So that looks like an ADT, and it is an ADT. So once you add type parameters to enums, you get abstract algebraic data types. So this is very nice. That gives you essentially a concise way to define ADTs, which previously you had to do like this. So that was the way you would write it, and that's in fact the way the compiler would expand the enum that you've seen for you. So you would get a base class, a sealed abstract class option, and then in the companion object there are 2 subcases. A case class, actually it's a final case class, so the final gets added here, that extends option, and well, you would probably have written a case object, but it turns out you can just write a normal value, val none, and that gives you an option nothing. But it doesn't stop here either. So we cannot just do ADTs, we can even do GADTs. So here's the example of that. So we have a tree of T, that's our enum, so T would be the type of the tree. And then you have cases where each case specifies a different value for the type. So true would be a tree of Boolean, false is the same. Is 0 given an n of tree int gives you a tree of Boolean. And if, for instance, given a tree of Boolean, the condition, and then 2 trees of T's gives you a tree of T. So that gives you a very natural way to write GADTs. And that means that we have now in one construct a thing that can really grow in the very typical Scala for scalable tradition, not for stairs. Well, stairs is sort of, yeah, you can also go up. That essentially can grow with you from very simple enumerations, colors, all the way to full-blown GADTs like trees, which I believe currently makes Scala the first language that can do all this. I heard that the Swift people have seen it and have just about thought that they might want to do something like this as well. Okay, so the public vote, what did people say? Well, they very much agreed with that. Enums make it. 56% thought enums are the nicest feature for beginners. The other 2 top-level definitions was in 3rd place, and drop new was in 3rd place. And the one that got 5% was actually a misspelling that should have been called infix and alpha, to mark infix operations and to have alpha annotations for symbolic operators. But that even got 5%, even though it was completely misleading what it would be. So why enums? Lots of use cases, and they're becoming more common. Avoids boring, repetitive boilerplate, and it can grow from very simple to very powerful. Okay, so that was my chapter on beginners. What about everyday coding? What's the nicest features for everyday coding? I think there are lots of candidates, and it's really hard to come up with a short list, but I'll try nevertheless. So number 3 for me is union types. So a union type gives you an ad hoc combination of types, that a type can be one thing or another thing. You don't have to put this in an either, or you don't have to write essentially a base class for this with subcases. You can just take 2 unrelated types and combine them with an or. So here's an example. Let's say we have 2 case classes. One is a username and the other is a password, and they're not related. And then we have essentially the help thing, where the help says, well, we have an ID which is given by a username or a password, and depending on whether it's one or the other, you do one thing or the other. So you can, the typical way to decompose, to deal with a union type, is to pattern match on it. So you just say, is it one thing or is it the other thing? And what's nice about it in some situations is that the union types, they have a natural subset and subtyping relationship. So a union type with more choices is a subtype of a union type with fewer choices, and you can play with that and use that. The other nice feature is that union types have no boxing overhead. These things, given that you start with already essentially box types, reference types, then taking the union of 2 reference types, there's no third object created. It's just one object or the other. So in cases where efficiency is very important, that's the most natural representation. Union types work also for singleton types. So you have here, for instance, a type command, which has 3 singleton types, so 3 strings. You say a command is the string click or drag or key pressed, and then you can essentially pattern match on that and find out which one of these it is. So all these things are great, in particular also for JS interop, because union types are informally in a lot of JavaScript code, and the TypeScript language has something that looks very much like that. So essentially, the way people add types to JavaScript programs very much goes via union types. So it's good for that, but it's not only good for that. It's good for a lot of other modeling situations. Okay, so if that was number 3, and that was already pretty good, what's number 2? So for me, number 2 would be extension methods. So extension methods replace implicit classes and make it easier to add methods to existing classes. So here's an example where, let's say you want to support usage like this one here, which is actually supported in the standard library. But how would you do that? So there's a string hello, and you want to write hello 3 times. So hello times 3. So how do you add this times operation with the asterisk to a string? So previously, the way it would work is you would essentially define an implicit class, a so-called decorator, that takes a string as argument and adds a star method, and then that class would essentially, the constructor of that class would be inserted automatically as an implicit conversion when there is the asterisk operation, and that way it would all work out. That works, but it's all a bit indirect, and these implicit classes and these conversions, they are the way to construct it is sometimes a bit clunky. That actually turns out to be particularly bad for if you want to pair infix operations with type classes. There are frameworks, macro-based frameworks like Simulacrum that you then have to use, which are very, very heavyweight. It's really difficult to make this all work. And with extension methods, it becomes very, very natural, and something like Simulacrum is no longer needed. So extension methods, the way you do it is essentially you just write a parameter in front of the method name. So the method name is the asterisk, and then you would say, well, the first string here actually goes in front of the asterisk, not after. So that's how you write it. So there's a string before and an int after, and then the code is just as you would write the usual repetition operator for the asterisk. And to get an extension method like that, one way to do it is you have to import the enclosing object. So once the extension method is in scope, you can apply it in fix like that. So that's the idea here. Okay, number 1 for everyday coding is the redesigned implicits. And we went through many variants of this, but I believe now we have settled it, and everybody that I've talked to is reasonably happy with this, which means that I think we're done, because before some people were always violently opposed. So the new thing is called givens. Givens replace implicit as a modifier, which we have in current Scala. They don't rely on names, which are often obscure for implicits, and they work very hard to press intent instead of mechanism. So to give you an example, here's sort of the standard example how you would do type classes, the ordering, the or ordering type class, where you say, okay, we have a trait, ord, which has, in this case, extension methods, a compare to method, and a less than method. And then the less than method uses compare to is left abstract. And then you want to say ints are ordered. And the way you do that is that you say given an ordering of int, so that's a statement. So there's an ordering of int that's given, and here you have to fill in the blanks to say, well, here's its compare to methods. And then once you have that, then you can use it with a maximum method here that essentially takes the ord as a given parameter. So if you want to see what's the delta to current implicits, then from what you've seen so far, it's that you write given instead of implicit for the parameter, and you write given instead of implicit for the instance definition, and furthermore, given is essentially a definition by itself. It's not a modifier for something else. Actually, it turns out that for the ordering example, it's quite complicated because depending on the type, it's either an object or it's a combination of a def and a class, and you have to know that how to construct all these things. Whereas with the syntax here, it's immediately obvious for all types how to set up a type class instance for the type. Okay, so here's another example, monoid. the way that would be constructed is like this, that you say, okay, again, you define type classes with traits. They can have extension methods for infix things. And then the instances would just be givens again. So you say there's a given, a monoid of string, and here's the combine method, and then you can use it in the sum method like that. So it provides a really nice syntax for type classes, which is much, much less cumbersome and boilerplatey than the current way people have to express this. Okay, the other thing givens do is that they tame implicit conversions. So an implicit conversion is currently you write it like this, and that is fine, except that it's actually too easy. So what's wrong with it? Well, it's too easy to write compared to how dangerous it is. The problem is with implicit conversion, it's a slippery slope. If you have one or two tasteful conversions, it can make your program nicer, shorter, possibly even more understandable. But you add more and more to them, and it reverses itself. Your program becomes essentially a mess of unpredictable conversions, and people stop understanding what happens. So that's sort of the big danger with implicit conversions. And for that, it just looks too simple, which meant that previously, when people introduced implicits in almost all tutorials I know of, people start with implicit conversions. And then they introduce implicit parameters and type classes and the like. But implicit conversions is sort of the one thing to say, well, wait a minute, that's the one thing you should probably not use. So I think it's a bad idea and to start with them. And why do you start with them? Well, because it's sort of the most obvious and easy thing. And also historically, that's actually how implicits came about. But we shouldn't be tied down to history. And we should be able to learn and see how we can do things better. Okay, so now implicit as a modifier will go away, and with it, this kind of conversion. So we can't do that anymore. So what do we do instead? So what we do is what some other languages do as well. I'm thinking of Haskell or Rust. There's a specific conversion class. So there's a conversion class in Scala called string conversion. You give it the type to convert from and to. And to get a conversion, you have to define a given for the conversion. So then you have essentially an implicit value. So you define it like this. Or you can make it slightly shorter. You can define it like this, just as an alias given. So you say given conversion string to token equals new keyword. It's not much longer than before, but it makes it clear that conversions are a special case of the general thing, which is to define a type class. I define a type class, and conversion is a special type class in that it essentially can convert from one type to the other automatically, but the mode of thinking should be I define instances of type classes. Okay, so what did the public vote say? So the public vote didn't agree with this judgment at the time. So they picked union types first, extension method second, and revised implicit third. So revised implicit is essentially the givens that I've shown you now. Good, so why do I think givens are so great? So what gives for givens? I think implicits are Scala's most distinguished feature. Where with distinguished, I mean it makes Scala, is the feature that makes Scala most different from other languages. Because not many languages have, or no other language has implicits, of course, exactly the way Scala does. And not many languages have something that is fairly similar. But there are also Scala's most controversial features, because we have seen in many cases that there are code bases where there can be a problem. And I believe givens are a far simpler and safer alternative. They emphasize intent over mechanism. So the intent is essentially I want to make something available for term inference. Givens, implicits are essentially just a way to say I won't bother writing this expression. Let the compiler define that expression for me based on the type that I give. So I say I want an expression of this type, and the compiler will produce that expression for me, and of course that must be unambiguous, otherwise it wouldn't work. So this idea to say I want to essentially have certain things, I want to demand and provide certain things that essentially get inferred by the compiler. That's the intent. The mechanism is then whether there should be an object or a val or a def or a combination of def and classes or things like that. So that mechanism in essence doesn't really matter because I want the compiler to infer these things for me anyway. So, and with the givens, essentially, I can put myself on the higher level of abstraction and just state it that way. I believe they make that way the idea of term inference much more accessible, and they discourage abuses like we've seen conversions, and there's another one with imports. The other thing is why what other improvements are there, and there's actually a long list about them. The most important one, I think, is names don't matter anymore. So in fact, all these givens, the givens that we've seen, they were all anonymous. They didn't, the value didn't even have a name. Turns out you can give them names if you want so, and if you care, let's say, about name stability over multiple versions, that might be a good idea, but you don't have to. So names don't matter in this whole thing, whereas previously they did in many different ways. Nesting is significant, which means that it turns out local coherence is really easy that way. There are no shadowing problems. There's a restricted implicit scope that avoids some surprises that people had previously. There's more robust prioritization, no accidental conversions, and better error messages. So actually quite a lot, quite a big package to make it work better. So then the question is, well, why didn't you just call them implicit and keep all that? Well, I think the main thing is that some of the things we do require a synchronization between library and user and library provider. So for instance, when I call a new given with an explicit argument, I have to mark that argument also with a given explicitly. So I have to match up calls, formal and actual parameter calls. And that's not possible to do with the old syntax without essentially migrating the whole ecosystem from one to the other immediately, because, well, there will always be code out with the old implicits out there. And in fact, we will support the old implicits indefinitely for the time being. I don't really see a cutoff date at all yet. So that means we have to essentially work with the old and with the new. But for that thing, it's important to actually change the syntax so it's clear that which is which. The hardest thing for these givens was actually naming them. So the design has been pretty solid for 9 months now, but how do we call these terms that get inferred for types? So we went through a long list of names. All these things have been implemented at some point or other in the past, but in the end we settled for given because it's essentially a nice short name, and it seems to capture the intent well. Okay, so let me go to experts. What's the nicest feature for experts? So since Scala 3 puts meta-programming on a new basis, there's actually lots to choose them, and it's difficult to pick a winner. But there's still some features that stand out. So for me, match types are really something that's really cool and really important. So match types let you compute with types without going through implicits. So you could previously compute with types, like let's say with shapeless, by essentially going through the implicit derivations and getting back things with new types. So that's the way you did it. But that's essentially a very complicated way to control it, and also it can lead to long compile times and lots of code generated. So those are the problems. So if you just want to compute with types, then there's a simpler way to do it, and that's essentially to just run computations, functional computations on the types. So here's an example. Let's say you have a enum tuple which has two things, empty and pair, and in fact the standard tuples in the libraries, they have that structure, only it's not called empty and pair, but just essentially tuple with and the empty tuple and the pair constructor. Then you can do a concat operation which takes two tuples, and then you can ask, well, the first tuple, what is it? Is it an empty tuple, in which case the concatenation of two tuples is the second tuple type. Is it a pair, in which case the concatenation is again a pair, whose first type is the first type of the first tuple, and whose remainder is this, so the rest of the first tuple and the second tuple. So that's essentially just like a normal computation, only now you do the computation on the types. Those match types, they can be recursive, and they're more straightforward to use than implicits. And there's work on type checking that's still in progress, so I think it's already quite usable. For instance, the new version of Shapeless uses these types extensively, but we hope to essentially improve it further so that it needs to use less casts in the libraries. So for the user level, typically you're fine, but often, so the problem right now is that if you have a value concat, so you actually do write a function that concatenates arbitrary generic tuples, which you also can do, then how do you specify that this function actually has your concat type? So that's where the compiler currently is not very good. So sometimes you have to help him and just say, believe me, by adding a cast. And we hope to reduce those casts until the time Scala 3 ships. Okay, number 2 for me would be type class derivation. The issue that we had so far was, well, type classes, we all know they're nice, they're cool, they're composable. You can add a type class after you've defined a type. You can parameterize it, make it depend on condition, and so on. But there was a price to pay, and that was that setting up these type classes for types was just much more complicated than just adding an extends clause. And in the future, that won't be the case anymore. So in the future, you can write, let's say you have this enum tree of T that well, that's actually another tree. And that, just like you can write extends some interfaces, you can say derives some traits which are type classes. And that will actually generate for you givens that essentially give you instances of these type classes, and then you have them. So all you have to do is derives ordering, derives pickling, derives show, and you have the implementations for that. So that's pretty cool. The derived methods internally use match types, inline, and macros to do their work, and I'll skip over that slide just to show it. That was just one concrete way to implement that. That shows how that works internally. So there is a low-level functionality that, well, there's the thing that maps derives to those derived methods, and then those derived methods get picked up by something. So the thing I've shown you here is a low-level way to do it, so you can actually produce generic code that can work for all case classes and sequences and types like that. Or you can use a framework for that. So there is Shapeless on Scala 3, Shapeless 3, which is essentially, again, a greatly simplified version of Shapeless, and also a version a lot more efficient than current Shapeless for Scala 3. Okay, so if that was number 2, what is number 1? So number 1 for me would be, well, I'm cheating here, that's sort of an envelope of features, functions everywhere. So Scala, as you know, distinguishes methods from functions. A method is not the same as a function value. And that's sort of inherent in the design of it. But what we can do is we can make them as equivalent as possible. And in Scala 3, actually, we add 3 fundamental capabilities that methods have to functions. So function types can, from now on, be dependent. So that means if you have a method, then you can have your result depend on the value of your parameter, right? So it's just with a path-dependent type. And with function types, with dependent function types, we now can do the same. So we can define a type like node extractor that takes a graph, and we call it G, and gives you back the node field of that graph, the node type field of that graph. So that's a dependent function type, and Scala 3 has it. Function types can also be polymorphic. So you can have a polymorphic identity as a type that says, given a type T, it's a function from T to T. Previously, you can of course write a method that has this type. The polymorphic identity is in pre-def. It's called identity, but you couldn't lift this method, the type of that method, into the type field and into the type space. And here you can do it. And the last one is that of course, methods can have implicit parameters, and so can types. So you can have a type executable of T, where you say it takes an implicit, a given parameter, given execution context, and it returns a type. And that by itself turns out to actually have huge implications for expressiveness and gives you a whole new dimension of structuring things. So what was the public vote? So the public vote said type class derivation. Implicit function types are one example of this types for everything, and match types came third. Cool. So let's put these things together in one example with synergies. So what I want to show is, what I want to do is, do you know about the ensuring predicate? It's actually in pre-def. So you have assert and you have require and you have ensuring. It's very underused. People should use it more because it's really quite cool. So what I want to write is syntax like list of 1, 2, 3. I want to sum, and then I want to essentially just add a predicate as a post condition to say I want to state something about the result. In this case, I want to state that the result equals 6. Currently, I couldn't do this because essentially, where does result come from? So I'd have to add a lambda here. I have to say ensuring result arrow result equals 6. But this result arrow is kind of annoying if you do this a lot. So the way we make this work is that we can have a result definition here, and it takes an implicit parameter, given parameter, that is of type wrap of T, and wrap of T is an opaque type in order to hide the representation so that the implicit only works on these things and not on general T's. Okay, and then the ensuring method would be, of course, an infix method. So it takes an arbitrary T and a condition that if it has a wrap of T, gives you booleans. So, and what it does is it simply runs an assertion. It runs the condition. It says, okay, run the condition and pass the x, so the x value as an argument to the condition. So the x value is of type T, but because we are in post conditions, we know that T is wrap of T. Outside, we don't know that. But inside that object, we know that T is wrap of T, so it can pass for a wrap of T. So we can run the condition, and the condition at some point would call, like here, result. So that's this method here, and that demands a wrap of T. But we have one, of course, because that's the one given to the condition, and it's an implicit parameter. So we pass that, and everything works fine. Good. So I'm at the end of this tour. So you might ask yourself, is Scala 3 a new language? And the answer is, well, from what you've seen, yeah, probably, yes. And many language changes, including some feature removals, new constructs, improve user experience, onboarding, and the books definitely will have to be rewritten because there's so many fundamental things like a future learning Scala for Programmers book probably would put enums first and probably wouldn't use new at all, and all these things essentially would have to be in the textbooks. But on the other hand, it's not really a new language because it's still recognizably Scala. So you still see, well, this is Scala, it couldn't be anything else. All core constructs remain in place, and a large and very practical common subset between Scala 2 and Scala 3 exists. I should know that because our whole code base, the compiler, the tests, the IDEs, everything is actually written in this common subset. So it compiles with both Scala 2 and Scala 3, and we don't really feel constrained or anything. Furthermore, that means that programs can cross-build. So Dotty compiler, Scala test, both can be published compiled and published on Scala 2 or Scala 3. So I think the real answer is it's a process. So Scala 3 keeps most constructs of 2.13 alongside the new ones. Some constructs will be deprecated and phased out in the 3.x release train, so 3.1, 3.2, and so on. And that requires now some temporary duplication, but I believe the end result will be a more compact and regular language. So here are the biggest replacements that we can list here. So we say we have essentially top-level definitions, that can replace package objects, together with another thing I couldn't talk about called exports. Givens replace implicit defs, vals, objects, conversions, the whole package. Extension methods replace implicit classes. Then inline, staging, and match types are essentially our answer to metaprogramming, and they replace the current macros. So that some people react with uneasiness and say, why so many features at once? The answer is that Scala 3 is really when the books will be rewritten. So we need to get a feature in now if it affects the foundations, if it simplifies life, especially for learners, and if it replaces existing features. Because you wouldn't want to write a new book on Scala 3 and then in 3.1 there comes this other huge thing that makes things a lot simpler than before. Your book would be outdated immediately. You would want that in the book. So we want to put these things in now so that essentially people can concentrate to have everything in one place. So that means we prioritize for 3 foundations, simplifications for developers, and restrictions. And we do not essentially look at more ways to add power and expressiveness so much. So how to get there? There's a source compatibility for a large common subset. Rewrite tools can handle much of the rest. And I believe because of the types and also because of binary compatibility, the migration should be fairly straightforward and certainly much better than the example people often bring up with Python 2 versus 3. So binary compatibility, just some words. Already today, the Scala 3 Dotty can link with Scala 2.12 and Scala 2.13 from now on. Right now it's 2.12. We'll switch to 2.13 probably by 3.0 M1. It can link with Scala 2.12 class files. So for instance, we run with the 2.12 standard library, and we can run with 2.12 Scala check and whatever. So it can transparently use these things. So you can put a Dotty module on top of a Scala 2 module. In the future, what we are currently working on is to go the other way. So to also have Scala 2 programs that consume new Dotty libraries, and that to make that work transparently as well. And so we have just started work in the Scala Center to do that. And that is essentially the promise to deliver that is based on having these tasty trees, which essentially are a complete representation of a Scala 3 program. And the idea is to make them available to Scala 2 as well, and not just to Scala 3. Okay. So the binary compatibility for Scala 3, the idea is to keep the tasty format binary compatible for the whole 3.x series. So that's a period much longer than the current 2-year release cycle. That's maybe 5 years, 10 years, something like that. So we want to take that much more seriously than before, at least after 3.1, 3.0, maybe we have still some breakages. Compile from Tasty then allows code to migrate without the current problems of binary compatibility. So there the idea is that you can publish an artifact with just the Tasty format, and then you can essentially map that transparently to whatever version of Java you have, or maybe JavaScript, or maybe native or something else. So that's the dream, that's the plan where we want to get. So you can try it out today, of course. It's dotty.epfl.ch. And that brings me to the end of my talk. Thank you.
Well, thank you so much, Martin. We have time for 2 questions. So, yeah, now I can see you. So if anybody has questions, we'll come to you with a mic. There you go.
Hi, thank you for the presentation. Can be used unit types for having completely null safety? And
yes.
it's something you want to do because it makes interoperability with Java very cumbersome.
Very good question, yeah. Yes, the answer is yes. There's obviously work to be done so essentially null safety to say, to represent types with nulls. The idea is the type string in the future would be just the type string without null, and to get a string with nulls, you write string or null, the null type. So unit types give you a very natural expression of null safety, and there's actually work going on by Abel Nieto, who's a student of André Lotak at the University of Waterloo, to actually make that happen. It's quite far progressed. There's a pull request that is in state to be reviewed and revised, but we hopefully we will get that in by 3.0. But since it's not our work, but independent work done at Waterloo, I cannot firmly promise it. I can just say that we are looking at that with a lot of interest, and hopefully it will make it in time. Yeah.
Thank you.
Hi, thanks for presentation. My question is about givens and implicits. So with implicits, it's the usual experience that if you use them too much together with the macros, your program will start to compile slow, and like it's a major pain point. So for instance, if I migrate to Scala 2.13 and then I replace all my implicits with givens, should I expect my program to compile faster?
That's a good question. I think it's often a combination of macros and implicits, like you say. So the macros will go away. So you will have to find something else for the macros. If you port your macros to the new thing, then the question is, will it be faster or not? I would hope it will be faster because essentially we have worked on the implicit resolution algorithms and also on the staging in the macros, which is now all fully typed. So essentially it's more rigid, it's more principle, and hopefully it will turn out to be faster, but the proof is in the pudding, so one has to do it and find out what happens. The other thing I could say is that, well, since a lot of time one uses implicits for type computations, I believe match types will help, because you can express them in a more direct way that way.
Okay, thank you.
Okay, one very last question. Okay, sorry.
Oh, hi. What type of optimizations would you foresee with keeping tasty?
Okay, yeah, good question as well, yeah. Keeping tasty gives you, since you have essentially all the code of your project, you can do whole program optimizations. There was once a project by Dimitri Petrashko to do essentially a whole program optimizer and analyzer. That didn't make it to the finish line. But I mean, we've learned quite a lot of things from that. So we're currently looking at static analysis that help you with essentially, for the moment, it's more correctness than optimization, but we could also use it for optimization. For instance, there's work by Feng Jung, another PhD student in my group, to use that tasty for proving once and for all that your programs won't have initialization errors, which is the problem that if you initialize things and sometimes they are null, and currently you can check that at runtime, but it's expensive to do that, to verify missing initializations. So that can be done with a static analysis, and that analysis actually has to look at the tasty code to see what the constructors actually do, and because it's a problem that where you have to pull several classes together to see whether in a class hierarchy everything is correctly initialized.
Thanks.
Okay, thank you again, Martin.
Okay, thank you.